guess we're good to go. So welcome to the Rust intro session at DevVox. I was surprised when this talk was approved, but I needed to try to bring Rust because I am a Java developer, and I've been trying Rust for 1.5 years, something like that, and I'm really impressed with some of the features that I could find in this language. My name is Hanneli. I am from Brazil, kind of a little bit far from here. I started the Brazilian Rust meetup in 2015, a while ago. I write software for this company called CodeMiner42. Quick disclaimer here, let's set some expectations. This is a session about Rust features. This is not going to be a tutorial about Rust. It's going to be more about the theory behind the language and why things work in a different way for Rust and for Java, for example. I'll be comparing both of the languages because I guess everyone here is quite familiar with Java, and that's going to make the process easier to handle with along the presentation. So we're going to see some GIFs because I like GIFs. And it's, early in the morning before lunch, so we all deserve GIFs. So I'm going to leave some references for those who are really interested into jumping into the language. But this is not meant to be a language war. I guess we both can benefit from different resources from different languages. So that being said, what is Rust? What is Rust? Come on, talk to me. A language. So if you go to Wikipedia, you get this interesting and super meaningful description. Rust is a general-purpose programming language compiled, strong and static typed, sponsored by Mozilla Research. It is designed to be safe, concurrent, practical language, supporting functional and imperative procedural paradigms. It's like wonderful. We all know everything about Rust now. It's like when you go to Wikipedia to try to understand more about something, and you end up understanding about anything, and more than that, you start questioning your own existence. Like, what? So Rust is not yet another language built on the top of the JVM. That needs to be clear. A while ago, I went to a Java conference to talk about Rust, and everyone thought that Rust, or almost everyone thought, that Rust was another language on the top of the JVM, and they were asking, oh, how can we compare Rust to Groovy in terms of bytecode? And I was like, no, wait. So that needs to be clear from the beginning. Let's talk about why we could consider Rust as a language to use in a real project. I don't know about you, but I have worked with embedded systems for a while. And sometimes, due to hardware restrictions or so, I wasn't able to use Java. Well, we can, sometimes we have restrictions. So if you can't use Java, which is a language that I assume you're all familiar with, which language would you choose to work with embedded systems? To think about hardware with memory limitations, and sometimes you can't flush things into a disk, you need performance. What would you choose? We could think about C or C++, and that's the most common choice that I've seen through embedded system projects. Sometimes C and C++ are great, but if you're coming from an exclusive Java background, it could be a little challenging to debug it, right? Especially if the team is not familiar with C++ templates and template hell or things like that. It could also be difficult to maintain the code. Sometimes the language helps you to write a better code, a code that it's easier to maintain, and sometimes it doesn't help you. And from my experience, it's challenging to keep good code for C++. It's very easy to mess up and come with code from different templates and things like that. Another challenge is manual memory allocation, right? Raise your hands if you never forget to call free. You never forget to do that, not once in your life. Well, I do that all the time when I write C++. But again, depending on the team, manual memory management can be a problem. So sometimes C or C++ can be a little bit inconvenient depending on your team and on the type of the project that you are working on. So in terms of a language, a good language to help us on the development process would be a language that doesn't force us to do a manual memory management, would be a strong and static typed language, preferably compiled, something that we can achieve performance results for embedded systems, something that we could reduce the number of runtime errors, a language that is preferably open source, because we could have a community around it, helping to maintain it, helping to fix bugs, helping to spread knowledge. Those are the features that we might be looking for in a language. So that's when I met Rust. Rust met all those requirements here, and along this presentation, I'm going to explain you why. So let's take a look into a quick overview of Rust structures. Have you ever tried to write some code in Rust? Is anyone in this room totally new to Rust? Most of you are, so I'm prepared for that. So let's have a very quick 5-minute tutorial about how we write code in Rust, and then you can get the general feeling, the sense of this language. So here's our function main, equivalent to public set void main, right? And again, like a good programmer, I need to write the FizzBuzz in a language to feel how it looks like. So let's write the FizzBuzz. Is everyone in this room not familiar with FizzBuzz? Not familiar with FizzBuzz? So FizzBuzz gives you the idea of printing a sequence of numbers. And if this number is multiple of 3, you print fizz. If the number is multiple of 5, you print buzz. And if the number is multiple of 3 and 5, you print FizzBuzz. So from a sequence starting in 1, going up to 10, or let's use 10, I would print 1, 2, fizz, 5, 6, 7, 8, 9, 10. Sorry, 1, 2, fizz, 4, buzz, 6, 7, 8. Sorry, I can't do that from the top of my head, but I got the idea. And then when I reach 15, I have to print FizzBuzz. Does it make sense? Besides my terrible debugging and test running mode. So let's try to write a function that performs this simple action of getting a number, checking if it's multiple 3, 5, or 3 and 5, and then actually printing something to replace the number itself. All right? So in our function main, we call a function FizzBuzz. And in Rust, we come with the name of the function, right? And then we define fn for a function. And then what are the parameters that I should pass here? Tell me. An integer. And in Rust, we need to specify the type of the parameter. So in this case, an integer is an U32, unsigned 32 bits. We have different sizes as well, but that's the most common one, right? So what do you need to do now? We need to iterate over this number we are passing here, right? And then we can just delegate this logic to another function that actually is going to perform the FizzBuzz. So let's write this function. Tell me, what are going to be the parameters, the arguments of this function? Another integer, another U32, right? And what should I do now? I'm sorry to give you a programming challenge early in the morning, but that's not the most difficult ones. Reversing red-black trees is much more difficult. So we basically are going to add this ugly stuff. It's not the best code that I can produce, but it's what you do in order to try a language. So if the number is divisible by 15, which means it's both multiple of 3 and 5, you print FizzBuzz. If it's by 3, you print fizz, and if it's by 5, you print buzz. And if it's any other of these alternatives, you just print the number itself. Okay, does it make sense? Does the syntax make sense? I think so. The only missing thing here is implementing the function is divisible by. What are going to be the parameters of this function? The number itself and the number you're trying to divide. So from there, it's pretty much straightforward. You just do an if clause, and you get the rest of the division. All right? Are we all set? Yeah, we are. So we implemented the fizz bus, and with that, we can understand some basics of the Rust language. First one, we need to specify the types. So it's strong typed. We also need to specify the type of the return of a function or a method. So for example, is divisible by is to return a Boolean, right? And we do that by using the arrow. We saw a basic for loop. We also saw if-else clauses. And it's important to notice that Rust has a limited type inference. So you can come up with a number or a string. Sometimes you don't need to declare the type, but when you have functions, you need to make it explicit, right? Another interesting information that you have in Rust is, can you see those macros? So the language has macros to help you to be a little bit less verbose. The same thing that you have in Java, Rust is as verbose as Java is, sometimes a little bit more. So you can come up with macros to help you to reduce the number of code that you actually write. So let's continue with some interesting information interesting concept that you have in Rust. In Java, are we allowed to do that? You come up with a variable and then you add +1. Well, in Rust, and that's probably one of the first things that you try in a language, but that's going to give you a compiler error. And then like you just downloaded the language and you try to write this 1 + 1, and then you cry because the compiler yells at you, say, don't do that, bad boy. So in Rust, everything is immutable by default, which means that if you really want to make mutability explicit, you need to use a keyword saying, hey, I am aware that I want to change this value, and I'm going to add the mute reference here. So this way, if you have a mute value, we can actually change and add +1. Okay? So everything is immutable. And there is a good reason for that. Let's go through another overview really quick. Another programming challenge for you. We want to find the sum of all the squared odd numbers under 1,000. Difficult? No, we can make it. Even early in the morning, we can make it. So first thing I did was defining a function called isOdd that gets a number and checks if it's odd, right? We define an upper limit, and then we can do some sort of functional programming here. We come with the sum of squared odd numbers, which is going to return us the sum. That's why it's U32, right? Then first thing we do, we get all natural numbers squared. Does it make sense? Do you like functional programming in Java? So we can pretty much follow the same concept. Below the upper limit, which we set here, right? That are odd. And then we fold them to sum, and then we print the result. Difficult? So Rust has high-order functions, and that can be pretty convenient, right? Other interesting features are tuples, enums, structs, traits. I'm not gonna go over through all of them. We are going to see traits by the end of the presentation, but that's not the main focus. So Rust has some features. Now that you had the sense of how the language works and how you organize your code and how you call some basic functions and pass parameters, Rust claims to be memory safe and data erase free, and having that immutability attached to the variable bindings is part of the key concepts to achieve memory safe and data erase free. You have a very smart compiler, and it's a very verbose compiler. If you do anything wrong in terms of types or in terms of assignments, the compiler is going to be yelling at you all the time and throwing you a bunch of compiler errors. But that's good because it reduces the number of runtime errors. So it's better to get an error at compiler time rather than getting it at runtime. It has a very good interface with C and C++, which means you can call native C and C++ functions. It has good generic support, which is pretty much similar to the one that we have in Java. Of course, it supports polymorphism. The community among Rust is very strong and active. Lots of the documentation were actually written by members of the community, and it's open source. So it meets a bunch of interesting requirements based on what we saw in the previous slides. And it has some bonus. Well, about the same level of verbosity as Java. And the compiler is also very verbose. Other interesting, and for me, those were like curious features about Rust, is the absence of a garbage collector. And if you have ever worked with embedded systems, sometimes the garbage collector can be inconvenient. So sometimes people claim that they're going to use C++ because there's no GC, but Rust has no GC as well. So how does it work? So every time I see a language that has no GC, I start praying and say, oh no, now I have to do manual memory management. And that's not really true. Rust has a bunch of features to prevent you doing manual memory management and provide you the absence of a garbage collector. So first of all, how do you achieve the safety? Rust claims that there are no segmentation faults. How do you achieve that? That's brave to claim that. So let's see some interesting features in Rust that actually prevent segmentation faults. So imagine this vector here. Can we actually do that? We saw an example before. Can we do that? You're getting a vector and getting another vector and passing it. If everything is immutable, can I do that? Yes? No. You can't. Because you're explicitly moving the value of a binding to another one. So when you have a binding, this is immutable and attached to what you defined. So you can't really do that. The Rust compiler is going to yell at you. And by this point, you're almost giving up on moving on to Rust because it looks like you can't do anything. So let's understand what's going on here. It's not unpractical. It's just a way to prevent memory errors and, again, to prevent segmentation faults. If you really want to share a reference, you need to tell the compiler. So do you remember, if we really want to have a mutable value, we had to use the specific keyword mute. The same thing is going to happen here. So if we really want to share a value, let's say with a function, we need to tell the compiler. So let's build this together. We have two vectors, and we need to call a function, passing the values of these vectors. But again, if we call this function and it pass a value, we are screwed up. The Rust compiler is not going to let you do that. So let's build this function. It's going to reduce the values of two vectors into a single integer. Okay? That's the goal of this function. So in order to do that, we need to get these vectors, sum them, and iterate of the values and actually come up with an integer. But at the moment that you pass the values of vector 1 and vector 2, the compiler is going to blow up. Because remember, the binding is actually attached to the variable. So you can't really do that. But in this case, you really want to do that. You know that your function is not going to harm your own code. So what do? So in Rust, you need to tell the compiler that I want to borrow this value to a function. And that's the meaning of this symbol here. You're telling, hey, compiler, I know what I'm doing, and I'm borrowing this value to a function. And you need, not only on the function, but you need to specify that on the arguments. You know that those arguments here are being borrowed. You lend them. Okay? Does it make sense? And again, that's a way to prevent memory management problems. So this function, this feature is called borrowing for obvious reasons. And you might be wondering, why is this thing done on this way? Have you ever heard of the read-writer's lock model? It's pretty common for distributed systems, for example. For those who are not familiar with, imagine that I have my vector1 here, and I have a bunch of readers asking, hey, v1, what's your value? Hey, v1, what's your value? So since the value here doesn't change, I'm safe to be telling what my value is. But what would it happen if a writer shows up trying to change the value? It wouldn't be safe anymore to provide the value of v1. So when you have a writer coming on, what really happens is like the writer kicks out the readers, get out of here. And now the writer can actually modify the value that you have here. Does it make sense? And when it's done, the writer goes away and the readers can go back and again ask for the value of a certain variable. That's the read-writing lock model. So in Rust, we have a similar memory model where we have either many readers or one single writer. And the readers, they do not require exclusive access. You can have a bunch of readers at the same time, but you can only have a single writer at a time. Okay? Does it make sense? That's why Rust can prevent seg faults, because it follows this policy. So in Rust, again, you have the base type that owns a value that's immutable. Remember, we just saw the borrowing. And the borrowing is a shared reader. And when you have the mute, it's an exclusive writer. Does it make sense now? Why you have all these keywords and how they are combined together? Then when you have the mute, then you have a mutable reference. And remember, mutable references need to be exclusive. So imagine that you have this code here. You have a mutable reference, right? And then you have this, and you're borrowing a mutable reference. What do you think is going to happen? Does it look good? Remember, you have either a single writer or shared readers. So that looks totally wrong, right? And that's really wrong. And the compiler is going to be yelling at you, what the hell are you doing? Stop. So the compiler is going to prevent you from doing most of these mistakes with memory management. So borrowing prevents iteratory validation, data race problems, trying to use a variable after freeing it, and so on. Does this memory model make sense to you up to now? We are still missing some things. If the Rust has no GC, how do you get rid of all these variables? We are missing that. And it could be very easy to mess up with borrowing if you don't know for how long a variable is available to you. So that sounds terrible. But no, you don't have to handle memory allocation manually in Rust, like I said. There is another strategy that's pretty convenient before you give up and say, no, that's too difficult for me. So let's see a little bit of lifetime in Rust. So every time you start a function, the function itself has a lifetime. And once you declare a binding here, the binding is going to live from the moment you declare this on this line until the end of the function. We know that. So for instance, which one is going to live longer, A1 or A2? Hi. A1 lives longer than A2 because A1 was declared after, and so on and so on. Does it make sense? We know that this variable binding, it starts living here, and it ends by the end of the function. So everything, every inner function here is going to keep these variables alive because the outer function is not finished yet. And by the end of the function, the lifetime is over. Death. Massive death. Destruction. You can't access that anymore. Does it make sense? That's why it's important to keep that in mind. It's when it's your flag sign to tell you when you can use a variable or not. So, you can also make the lifetimes explicit in Rust. Let's say you want to make sure that B1 is going to live enough to reach this function, but not this function. How can you make lifetime shorter? So you have some control over the lifetime by making them explicit on the function calls. So every time you pass a parameter to a function, you can also make the lifetime explicit. You can also have multiple lifetimes for every parameter that you have. And turns out that's pretty convenient if you want to have a fine-grained memory management. Right? Does it make sense? You can control the lifetime here. And by the end of the lifetime, of course, a variable is free. So with lifetime, the GC is not really necessary anymore because we have an idea of how much every variable is going to live. And we know that after that lifetime, no one can access that variable. And turns out that's a very good mechanism to avoid dangling pointers. I've done lots of Objective-C, and I was always running into dangling pointers. And turns out that that's a difficult issue to notice that you're going to have. And Rust is very good to prevent dangling pointers. Of course, no manual memory allocation nor free. You just need to be aware of the lifetime of your function. So is Rust always safe? That's one thing that I ask myself. And by following the ideas of borrowing, immutability, and lifetimes, it is pretty safe. However, you can explore other areas by interfacing with C++, and then Rust is not going to be that safe. Okay? Before we talk about safety, let's go through a quick comparison between Rust and Java, and then, if you want, we can jump into the interfacing with C++, because I think that's quite interesting. So Rust has a good generics system. It's pretty much similar to the one that we have in Java. It also has traits, pretty much like Scala has. So let's compare some classes in Java. This is a random class in Java. And this is how it looks like in Rust. We don't really have classes itself. We have something similar to C and C++, where you have a struct and an implementation for that, right? Does it make sense? You have the fields in one place and the methods in the other, right? That's pretty much how we can compare both languages. Both have primitive types, both Java and Rust. If we want to write an interface, that would be something like that. And here's an interface for Java 8. Here's a trait for Rust. And we can explore some concepts for interfaces. Notice that we can have a trait, so we can implement a certain animal for the trait, and we can implement the same animal for without being bound to the trait. That's something powerful that Rust has. So you can bound multiple structures to interfaces, to different interfaces, and have the same type without being bound to an interface. So if you notice, I have animal here, and I have horse, and I have like this horse following this contract, but this horse doesn't follow the contract, and they are both horses, one following the contract and the other one not following it. So that's a feature that you could try to achieve by giving different names for interfaces in Java, but I don't think there's a real one-on-one equivalence. And the generics are my favorite part because they are much shorter. And the syntax for Rust generics, for me, it's a little bit better to manage. It's not that convenient when you're managing lifetimes for generics, because then you have to make the lifetimes explicit. But it tends to be a little bit shorter than Java. Here is a more complex example with upper and lower bounds. Same idea that Scala, or even a little bit different. You are specifying the classes that are bounding individually, not in a group of subclasses. It's not really an upper bound. You're just throwing the classes that you're going to allow here. So I think I have a few minutes left, and I would like to talk a little bit about Rust interfacing with C++ and C. And that's when things can get complicated because your sense of safety is compromised. Like I said, you can call native functions from C and C++ inside Rust, but when you do that, since the C and C++ are not really safe, they don't provide you lifetimes and borrowing and so on, you need to use this word unsafe. And that's when bad things can happen, because if you explicitly announce that you're being unsafe, then you can get dangling pointers and problems with segmentation faults and so on. So be very careful by using this directive here. When I was learning Rust, I used to add this involving my code because it would compile. So that's basically a directive that says, compiler, shut up. I know what I'm doing. However, it can bring you a bunch of problems. So use that wisely. I've been doing some Rust pet projects, and the best way that I have found to use unsafe is for native calls. And I always wrap them in another function that I have control over. So if you have an unsafe call, wrap it up into an external function. In other words, don't do that. Don't open your main and then throw your code in there and then expect everything to be fine, because it won't be. So, is Rust perfect? Of course not. And I would like to tell you a little bit about the downsides of the language. Of course, I'm kind of evangelizing the language because I think it's helpful. But I felt some of the downsides of this language in some of my projects. The first thing that I noticed was about the learning curve, because, oh man, you get the language, you download the compiler, and then you try to bind a variable and add +1, and it doesn't compile. And then you try to pass a vector to a function, and it doesn't compile. So the learning curve is kind of frustrating. It was one of the most difficult languages that I tried to learn in a short amount of time, and it was really challenging. For me, I got lots of new concepts. I wasn't familiar with lifetimes at all, and it took me a while to understand how it works. And it took me a while to understand why my code wasn't working, or why my code is working, which is even worse. That was a pretty new language. I mean, it's been developed since 8 years ago. However, it just came out as a popular language in the last 3 or 4 years. So it's pretty new. So the amount of questions on Stack Overflow was quite reduced when I tried Rust for the first time. So that was quite challenging. So I think the community really helped on the process to make all these 3 points smoother. Like I said, they tried to come up with better docs. So for instance, Mozilla reached a campaign to encourage people to improve the docs, and it turned out pretty well. The docs are much better nowadays. By starting meetups, I noticed that other people around me were trying to learn Rust, and we started studying together to try to figure out how to solve some of our problems. And last but not least, the tools. So when I started playing with Rust, it was only the language. And then they came out with Cargo, which is like a Maven for managing dependencies and libraries in Rust, which is pretty convenient. And then after coming up with Cargo, lots of people started creating their own libraries and sharing it. So nowadays, you can do a bunch of things in Rust, starting with web development, going to, I don't know, linear algebra with n-dimensional matrices. If you want to do something like that, there is a library in Rust. Going to genetic algorithms and things like that, which is pretty amazing. For a 4-year-old language, having the amount of resources that Rust has is quite impressive. And I'm not even counting things that focus on hardware and embedded systems, because you are going to find a ton of things on GitHub. Starting with drone firmwares written in Rust or things like that. So this engagement that the community has with the language really helps you to jump into a real project and get something done with Rust. Even though like the learning curve is not the best, having active and interesting projects, it really helps you to get something by the end of the day. So, quick bonus. How do you describe the Rust type system? Following this, this is a PhD thesis I was reading, and that's quite interesting. There was someone that's doing his PhD, and he's trying to formalize the Rust type system. That was quite challenging, actually. And I would classify it as static and somewhat strong for most cases, pretty much like Java, static and somewhat strong. Comparison, which one is faster, Rust or Java? So it turns out that Rust is much faster than Java for some particular problems. So if you get the well-known Mandelbrot algorithm, Rust is going to be, I don't know, more than 2 times faster than Java. And that's if you go like to the famous benchmarks game website, which is kind of a reference to benchmark different languages, you can see other different algorithms that Rust easily could beat Java. On the other hand, some of them are really bad. So if you get the K nucleotide, it's going to be much worse for Rust than in Java, for example. Those were between Rust 1.5 and Java 8. Some of the versions of Java 8, the most recent versions. So yeah, we can see like we have good and bad points of adopting Rust. Not everything is going to be faster. Here's a free gift for you, because you made it to the end of this presentation. So here are some references. This first one is a video about a tutorial if you want to jump into Rust. That's one of the best tutorials that I have ever seen, because it's not one of those slow tutorials where people say, now type this, now check this function. You just clone a repo, and then you can interact, and then you can follow the steps on the video. So that's pretty good. I also let you some external references. It's just a bunch of links, but the most important is the first one. And the last one, of course. Here is a good comparison between Java and Rust in terms of performance. I've been talking about Rust for a while. I have some talks for intro sessions with Rust and Pokemons. If you like Pokemons like I do, you can follow my tutorial by building Pokemons with Rust. I also delivered another talk about the Rust type system itself, if you're interested. I presented this at Python Brazil last year. And that's it. Special thanks for the Devox team who brought my Rust talk into this conference. And thank you very much for attending this session. We have 10 minutes and questions.
Hi. So first, thank you very much for an interesting talk, and the previous one too. So you talked about, when you talk about type safety and lifetimes, I could see how it would work if you have, stack allocated stuff and then, they go out of scope essentially at the end. How does it deal with something like a linked list where you don't know in advance how many elements you're going to have? How does it deal with in a kind of type safe way? Does that make sense?
Yes. So it doesn't have a linked list as a built-in type. You have arrays and vectors. But if you want to build that, remember that you always need to borrow your reference. So if you have a linked list, you have to borrow your previous reference. So you have to keep borrowing it. And if you try to access something that you didn't borrow, the compiler is going to blow up.
How do you allocate and deallocate nodes safely?
You don't do. It's not you that's going to deallocate it. So while the linked list is on the lifetime, you can safely access its members. Once the lifetime is over, you can't. And the compiler can evaluate if you try, at compiler time, it can evaluate if you're trying to reach something outside of the lifetime. Remember, it's a static type language, so it means that there is code tracing some stuff for you, and they can actually infer that the lifetime is valid or not. So think about that. When you compile, it's going to...
I get it, but you're implementing a linked list, right? And you need to say, okay, I'm going to remove this node, and I have to remove it and deallocate it. How do you
So
do
about
that?
the removal,
Yeah.
you don't get the same object. You need to copy the object, for example. That's how I would solve that.
You get a new linked list.
Yeah. That's the way to solve that. To remove it, you copy it.
Okay. I wouldn't need to read that part. Okay, thank you.
I think, I'm not sure about that, but there's probably a better way to do that without copying. Or like doing a backup of parts of your list, and then deallocating the rest. But the first thing that I would think about doing is copying, because things are immutable. And removing would be the case where you can't borrow, so we have to copy.
What do you personally use Rust for?
So I like maths, and I was personally trying to develop some linear algebra libraries for replacing some math code that I found in Octave. So I built it in Rust, and it actually became part of an open source project. I was helping some postgraduate students at the university that I graduated in. And we came up with some improvements for this linear algebra library. I gave a session at Rust Fest in Europe to talk about this library. So that's my particular interest for Rust. And turns out that the performance is much better. I've seen a bunch of people building embedded systems for drones, for robots, for IoT with Rust, because it can replace C and C++. And I saw lots of people who are tired of C++. It's not, well, it happens to some people, they get tired, and they try to find a new language, and they met Rust.
Thank you.
Any other questions? GIFs? All right, thank you very much. If you have any further questions, I'll be around.